Hi, my name is Biel. I am a senior at the Department of Physics at Washington University in St. Louis. The title of my presentation is Experimental Demonstration of Jarzynski Equality for a Driven Dissipative Qubit. And I worked on this project with Sarah Erdemar and Miriam Abbasi, and we were supervised by Dr. Kader March. Here is the outline of my talk. We'll begin by introducing Jarzynski equality, and thereafter we'll talk about our methods for our experiment, and lastly, we'll talk about our results, and these sub-bullet points I'll get to later. We begin by defining a process as an action that changes the system's parameters. For a pedagogical example, consider a piston, which is described by the parameters pressure, volume, and temperature. And when this piston undergoes compression, the value of pressure, volume, and temperature may change. And because compression has to change the value of the parameters, we consider compression to be a process. In an undergraduate thermodynamics class, we may consider this process we may assume that this process is quasi-static or that the process takes infinite amount of time, but realistically speaking, most processes are going to take finite amount of duration. And in such a case, we talk about the average work that we do on the system, and this can be greater than or equal to change in Helmholtz free energy. In 1996, Jarzynski came up with a new relation shown here. On the right, we have the average of e to the minus beta work, where beta is the inverse temperature or a value that is proportional to 1 over t. And this is equal to the right-hand side, which is e to the minus beta times change in Helmholtz free energy. So the significance of the latter statement is that the first relationship that we have is an inequality, whereas the bottom statement is equality, which places a tighter bound. What we want to know is whether this equality applies to non-Hermitian quantum systems, where a non-Hermitian system is, for our purposes, an open system that can have gain or loss in energy. And Defner and Sexton in 2015 published a paper that theoretically showed that, yes, this equality should hold. And on the left, we have a plot from their publication. On the x-axis, we have the parameters that they're changing. And on the y-axis, we have the Jarzynski equality, where they have moved the right-hand side to the left-hand side. And Jarzynski equality holds when this value equals to 1. And this is what they've shown here. We see that no matter how they change the parameters, they see that Jarzynski equality holds. However, this is for a special set of parameters that fall under what is called a PT symmetric regime. Once the parameter leaves this regime, it breaks the parity time symmetry. And this is a result that Defner and Sexton showed. The blue line is the real values, and the green line is the imaginary values. And we see that we do not get a real value of 1 once we break the PT symmetry. What we would like to do is to demonstrate that this holds experimentally. So we have talked about the Jarzynski equality, and we have talked about our motivation. Now let's talk about our methods. So we'll begin by talking about how we implemented a controlled dissipation, and we will also talk about our process, which would be varying the drive that is applied to the qubit. So to start us off, we realize a qubit with controlled dissipation using a qubit. To unpack what this means, we consider a quantum system with discrete energy levels, which we label G state, E state, so on and so forth. And because we're interested in qubit or quantum two-level system, we're going to look at just the bottom two levels, G state and E state. Population of the qubit might be all in the ground state, but when we apply a drive, we can send this to the E state. And if we continue to apply this drive, it will oscillate the population back and forth. And because it's the quantum system, we may also have a superposition of the state. And the strength of this drive, we label as J, and it determines how fast this oscillates. Because we're interested in non-Hermitian system, the energy may leave the system, and this decay rate is labeled gamma. But unfortunately, this decay often happens to a channel that we cannot account for. So to address this problem, instead of considering the bottom two levels, we're going to consider the first 3, which we call a qubit. And because we're still interested in a qubit, instead of taking the G state and the E state, we're going to take the E state and the F state, which will still have the drive. But now the benefit is that when the energy decays, it's going to decay to the ground state, which is something that we can monitor. And because we can monitor the ground state, we can find the value of the decay rate or gamma. So now let's talk about the process for our experiment. What a drive is applied to a qubit, it's Hamiltonian, is described with this 2x2 matrix. So the detuning, or the delta, is the frequency difference between the drive that we apply and the resonance frequency of the qubit. So when our drive is on resonance with the qubit, the detuning is going to be 0. Otherwise, when the frequencies are different, detuning will pick up some non-zero value. The gamma, once again, is a decay rate. We're going to set this fixed, so it's not a parameter of importance to us. And then the other parameters that we will be changing is the J, or the drive strength. What the Hamiltonian tells us is that when we apply a drive to the qubit now takes on a different energy values, which we label E plus and E minus, and they have their associated states plus and minus states. So note that the energies are a function of the parameters J and delta. So when we change one of these parameters, the energy is going to change. And it's much like how if we change the volume or the pressure of a piston, the energy of the piston changes. We can represent our combination of parameters in the parameter space. On the x-axis, we have the drive strength. On the y-axis, we have tuning. And there's a special point of interest to us where I have labeled with x, where the plus state is equal to the minus state. And we call this point the exceptional point, or the EP. And the reason why this is important to us is because it defines where the PT-symmetric regime is. So PT-symmetric regime is where the J value is greater than this EP point, and the detuning is 0. Once we pick up some kind of non-zero detuning, we break the PT symmetry. And this is important to us because Steffner has shown that Jarzynski equality really only holds in the PT symmetric regime. So we're going to consider 4 processes. The first one is a control case where we apply a drive with fixed J and a detuning of 0. And neither of these parameters are going to change over time. So this is a control case. And the next case is where we're going to apply the drive, but this time we're going to decrease the J a little bit and then return to its initial value. And both of these processes are PT symmetric processes. In contrast, our third and fourth processes where we positively or negatively vary tuning they break the PT symmetry. But for all 4 of these processes, we're always returning to the initial set of parameters. And what this ensures is that the change in Helmholtz free energy is going to be 0. And that means the right-hand side of the Jarzynski equality, or e to the minus beta times delta F, is going to be 1. So now that we have talked about our methods, let's delve into our results. So first, we confirm the Jarzynski equality for an arbitrary beta. So on the top left, I have put the parameters that we're using. We use a decay rate of about 6.68 inverse microsecond and duration of the loop of about 1 microsecond. And on the bottom left, I have put the parameter space with the color-coded processes for reference. On the right, we have our plot. The x-axis is the inverse temperature, or beta, with an arbitrary unit because we have normalized the work. And on the left, we have the average value of e to the minus beta work. And again, the Jarzynski equality holds when our values are 1. So for the first experiment, which are color-coded in blue and green, the simulation says the Jarzynski equality should hold as the plot is about 1. Oh, yes. The solid lines are experimental data and the dashed lines are a simulation. And we see that our simulation tells us for the first experiment that the e to the minus beta work is always 1. And our experimental results are pretty close, at least close relative to the other 2 cases where we have color-coded in black and red, where we gain detuning, therefore we break the Perry-time symmetry. And we see that Jarzynski equality does not hold for the last 2 experiments because of how far they deviate from 1. But the great thing about Jarzynski equality is that it should hold for process of any duration. So to test this, we change instead of changing the inverse temperature beta, we're going to change the duration of our process. Once again, on the top left, we have a decay rate of 6.68 microsecond or inverse microsecond. And then this time we set the beta to be fixed at 0.5 arbitrary units. So on the right, again, on the y-axis, we have average of e to the minus beta work. But on the x-axis, we have the time or the duration of our loop in terms of nanoseconds from 500 to 1,500 nanoseconds. So once again, considering the green color-coded experiments, the values fluctuate around 1, which tells us that Jarzynski equality holds for these 2 experiments. And that is what we expect to see since they are PT symmetric processes. On the other hand, when we look at the experiments color-coded in black and red, which are when we break the PT symmetry. Clearly, in general, they break the Jarzynski equality as they deviate from 1. So in summary, we have shown that Jarzynski equality holds for processes that conserve PT symmetry, but when the process breaks the PT symmetry, the equality no longer holds. And when it does hold, it holds for just about any duration. We chose our path into parameter space to be a loop to simplify the calculation, so that is, we wanted delta F to be 0, so that the right-hand side of the Jarzynski equality to be 1. But although our work still serves as a proof of principle experiment, more general process could be tested, where instead of returning to the initial parameters, we may stop at a different values of the parameters. Lastly, similar procedures could be applied to test the generalized Jarzynski equality, where an information term is introduced. And if we can somehow calculate that, we could use the similar procedures to test it. Before I conclude, I just want to give special thanks to the Department of Physics for providing the Diversity, Equity, and Inclusion Summer Research Fellowship, which allowed me to participate in this research. Thank you.